In this video series, we're going to start thinking about light and how light relates to electrons. So in the first set, let there be light, let's think about how light works, what it does, and everything else. So we are going to study light and how it functions in order to fully understand how an electron behaves. So at the end of this video series, we should be able to say, we believe the electron is here, and here's what it does. We're going to start by exploring the wave-particle duality of light. That means that light behaves as a particle and as a wave. And so the light that we see is what's called visible light. So this is light that is colored or white light. And so all light is a type of electromagnetic radiation. And in a vacuum, light moves at 2.998 times 10 to the 8th meters per second. We know that this is quite fast, and we know that it's faster than the speed of sound. So we know that because during a thunderstorm, you will see the lightning and then you will hear the thunder. And so this is true in all types of light and sound interactions. And so what do we need to know about light in order for light to be studied? So waves are characterized by their amplitude, wavelength, and frequency. This is true for both light and waves that you might find in water. So what is amplitude, wavelength, and frequency? So wavelength has the symbol lambda, and frequency is nu. So if we draw several waves, so I'm going to draw a couple of waves. So we're going to start with a red. These colors are meaningless, they're just colors. So we're going to start with one wave. And then we're going to draw two more waves. And we are all going to pretend that these waves are exactly the same up and down and everything else. So as we look at these waves, there's a couple of things. So this is quite busy, but let's see what we might already know. So we have amplitude, which is the height. And that equals the height. And so this is related to the intensity. So if we look at these two reds, so we have, let's bring that back. If we look at the red line and the red dotted line, this has a lower intensity. So dim light, or if you might think of bright red light and less bright red light, is the same of the both wavelength and frequency, but lower intensity. So it has a lower amplitude. So let's look at wavelength. So wavelength, it has units of meters. Typically, when we think about light, it's going to be in nanometers. So the traditional units are nanometers, but meters. And so this is measured as crest to crest. And so that means if you take this peak here all the way to this peak here, alternatively, you could, I'm going to use a green highlighter, measure the wavelength here for the other line. So these are both going to be wavelengths. And so we can see that the wavelength of the blue line, or the blue line, is smaller than the wavelength of the red line. So the other thing we're going to look at is frequency. So frequency is the symbol nu. The units are hertz, which is 1/second, or a per second. And so this is measured as the number of repeats, otherwise known as cycles, in a given time. So if we look at this graphic and we think about the number of cycles of the blue, so for our blue light, we have 1, 2, 3, 4 cycles. And for the red light, there are 2. So the difference of these basically tells us how many cycles or hertz there are in a specific time period, a second, as well as the frequency. So looking at this, it's quite easy if you were to have a time graphic or nanometers in order to measure these. But it turns out that we can also calculate this for lots of different lights. So frequency and wavelength are related to one another through the speed of light. So c is the speed of light, and this is 2.998 times 10 to the 8th meters per second. Lambda is the wavelength, usually in meters, or in order to cancel, it has to be in meters. This is the frequency, and this is in hertz, or per second. So we can calculate these. So all light has the same speed of 2.998 times 10 to the 8th, and the frequency and wavelength are related to one another. So what is the wavelength of light in nanometers for a barcode scanner with a frequency of 4.73 times 10 to the 14 hertz? So we can use the C equals lambda nu equation. We want to solve for lambda. So lambda is C over nu. So now we can plug this into, we can plug in our values. So we have 2.998 times 10 to the 8th meters per second divided by 4.73 times 10 to the 14 hertz, which is just per second. And that gives you 6.3 times 10 to the negative 7 meters. So we're going to multiply that by 1 times 10 to the 9th nanometers in 1 meter. And that gives you 634 nanometers by using the speed of light. So let's look at another example. So a green laser pointer has a wavelength of 525 nanometers, and what is the frequency of light in hertz? So if we know that C equals lambda nu, we're going to solve for the frequency, which is C over lambda. So if we plug in our values of 2.998 times 10 to the 8 meters per second divided by 525 nanometers. Now, meters and nanometers are related, but do not cancel without conversion. So there is 1 times 10 to the 9th nanometers in 1 meter. So when you plug this in, I get 5.71 times 10 to the 14 hertz. So as long as you are provided a wavelength and a frequency, we could calculate either or. We can calculate using the speed of light. So all light is part of this electromagnetic spectrum. And so if we look at this, we can see that the frequency changes in one direction, so the frequency increases in this direction, and the wavelength increases in this direction. So they are inversely proportional to one another. All light, whether it is radio waves or gamma rays, can be determined using lambda nu equals the speed of light. So they just have different amounts of energies, which is also related to one another. So as we start to look at lights and waves, let's think how waves interact with one another. So a wave, whether it's in a body of water or a light wave or a sound wave, is going to be able to interact in an additive, which is called constructive, or interfering, destructive way. So let's think about what that means. So if we have waves in phase, which means you have 2 waves, and mine are going to be mostly together, you're going to get, bigger waves. Because this plus this, the positive parts are the parts that go up, add together, and they're just bigger. So if they're out of phase, that is not a word, phase. If we have this wave and we have this wave added together, you're going to get a flat line. Because these waves are both perfectly similar, just out of phase. So everywhere where this one goes up, this one goes down. So when those two add together, there's no wave left. It becomes a flat line. So what about waves that are only partially in or out of phase? So if we have waves that kind of look like this, so we have the first wave, and a similar wave, or perhaps a wave of a different frequency, we're going to start to get other diffraction patterns. So you might see something where you have smaller waves followed by bigger waves. And so we're going to start to look at how these waves interfere or interact with one another based on their phases. So whether they have crests at the same time or not. So how can we think about the interference of waves? So one thing is we need to organize all of the waves we're going to study. So these are barriers with a single slit, and on the left side, we're going to look at waves. And on the right, we're going to look at a particle. So I'm going to draw a detector screen here. Basically, the detector says, what do we see at the end? So if we were to think about waves, so we're going to make those blue, kind of like water waves. So if we get the waves to come forward towards this barrier with a slit, some of the waves will be able to go through, and these waves will all be organized together. So what you'll see is a ripple. Rippling effect that kind of goes out in this direction. And so what we'll see, is a pattern where the greatest density of wave interaction is right in front, but you do see this interfering as things go forward. But what about if we have a particle? So we can think of a particle as if you were going to throw baseballs or ping pong balls or something else at a wall with a hole in it. So as you begin to throw different balls, what we'll see is that only some of them, in a rather Gaussian distribution, hit this wall. So there is a different pattern observed when you have particles or waves. So a very famous experiment is the double slit experiment. This means instead of having one slit, we're going to have two. And so this is going to allow us to even further study how waves and particles interact with each other. So again, we'll have waves on the left, particles on the right. And so as we look at the waves, we're going to have the same incidence where they come through. But what we'll see is that we get the same pattern, but on the other side. So when we hit our detector, we're again going to see an interference pattern where we can see that these waves interfere with one another. So let's look at our particles. So as we again throw different footballs or baseballs or really anything towards this wall, the only ones that make it through, and whoops, that's the wrong color, but that's all right, end up in this pattern where we can see and map directly where the slits are. So this is showing us that what would the behavior be if it was a particle or a wave. When light is shown in the double slit experiment, we observe this pattern. So that means that light can behave as a wave. However, the single and double slits confirmed that we have a wave. We have seen that some metals emit electrons, which is a particle, when light shines on them. So what do we see? What does that mean? If we have a metal block and we have light coming in, we can eject an electron. So This suggests that light has a particle-like behavior. The reason it suggests that is because when a wave hits a particle, the particle will ride the crest, but it won't be ejected. In order for an electron to be ejected, it must be hit with enough velocity in order to eject that object. So this phenomenon has been studied by many different scientists. It's called the photoelectric effect. So what is the photoelectric effect? So the first experiments were to vary both the wavelength of light and the intensity of light. So if we vary the wavelength and on the other side the intensity, what do we see? So what we see is that at some time period, we start getting electrons ejected. At a lower intensity, we actually see the same pattern, but less electrons are ejected. So at this threshold right here, which is a specific wavelength for a specific metal, the electrons are ejected. You don't tend to see a relationship where increasing wavelength increases the number of electrons you see. It just reaches a threshold and then moves from there. So we see that electrons are ejected above the threshold, but not below the threshold. Albert Einstein suggested that this light was behaving as a particle, which he named the quanta or a photon. So a single particle of light is considered a photon of light. So what does this mean? So Albert Einstein and Planck determined that they could calculate the energy of an ejected photon. Oops, that should say electron. Based on the wavelength of light that ejected the electron. So we can now, if we think about this drawing, we have the light coming in, oops, and we have the electron coming out. We know the wavelength of light. We can also determine the energy of the photon. So they were able to determine that the energy of a photon is equal to Planck's constant times the frequency. So Planck's constant is h, and that is 6.626 times 10 to the negative 34th joule seconds. So this value allows us to convert energy into frequency. And so if we also were more curious about the wavelength of light, the energy of the photon is equal to hc over lambda. So in order to convert from the first equation to the second, we were reminded that c equals lambda nu. So nu equals c over lambda. So we just replaced the c over lambda for frequency. So this equation and this phenomenon allowed Albert Einstein to determine or propose the photoelectric effect. This means that in order to eject an electron, it must have enough energy to overcome the work function, which is psi. This is unique for all metals, which means that the light that ejects an electron from metal A will be different for metal B. So the kinetic energy of the ejected electron is equal to the energy of the photon minus psi, which is the work function. So we can start to use this information in calculations. So a nitrogen gas laser pulse has a wavelength of 337 nanometers. What is the energy of one photon of this light in joules? So we need to remember that E photon is equal to hc over lambda, where h is 6.626 times 10 to the negative 34th joule seconds, multiplied by the speed of light, which is 2.998 times 10 to the 8th meters per second, divided by the wavelength of 337 nanometers. We need to convert that into meters. So in 1 times 10 to the 9th nanometers, there's 1 meter. So when we plug this in, we get that the energy of a photon is 5.89 times 10 to the negative 19 joules. So we can ask a follow-up question of, if a laser pulse contains 3.83 millijoules of energy, how many photons are in the pulse? So we're asking, how can we calculate this? So we're going to take our energy of 3.83 millijoules, divide that by 1,000, because there are 1,000 millijoules in 1 joule. And then we are going to multiply that by the reality that 1 photon has 5.89 times 10 to the negative 19 joules. When we plug this into our calculator, we should get there are 6.50 times 10 to the 15 photons. So in a single laser pulse, it has this many photons of energy. What about if we want to know the energy required to dislodge an electron from sodium metal is 275 kilojoules per mole? What wavelength of light in nanometers is required to eject electrons? So we know that lambda is equal to hc over E photon, which came from the equation that E photon is equal to hc over lambda. So I just rearranged that. But we need to figure out the energy in 1 photon, because this gives you the energy per mole. So we need to convert energy per mole into energy per photon. So we have 275 kilojoules per 1 mole of photons. Using Avogadro's number, we know that 1 mole of photons is 6.022 times 10 to the 23rd photons. So that gives you 4.57 times 10 to the negative 19th joules per photon. So now we can plug this into our equation, where lambda is equal to 6.626 times 10 to the negative 34th joule seconds, multiplied by 2.998 times 10 to the 8th meters per second, divided by the energy of this photon, which is 4.57 times 10 to the negative 19 joules. It asks for this in nanometers, so we're going to go ahead and add that in, where 1 times 10 to the 9th nanometers is in 1 meter, and that would give us 435 nanometer light. So all of this is to say that all light is related to each other using the speed of light. We can also determine the energy of any photon of light.